if you have a large, like a size of input for a small buffer, then the content of memory will be overwritten. Then in this case, the system may crash. But actually, buffer overflow is more powerful, much more powerful than just crashing the system. So we will see some example. In particular, we can use buffer overflow to inject, for example, some malicious code and run the malicious code, right? So we will see how this can happen, right? So you can, for example, if you have a program, you can actually invoke some additional function. The program originally will only execute function A, but you can actually invoke function B, which is not supposed to be executed by the program. Or, as I said, you can inject some malicious code into the memory and run the malicious code. So all these kind of attacks can be done using buffer overflow instead of just crashing the system. Okay, so we will look at how this can be performed, what are the general technique used by the attacker to launch this buffer overflow. So first of all, let's look at some basic concept. So we will look at what is a buffer and what does buffer overflow mean, and then how does the operating system manage the memory. So this is important because if we can identify where are the critical content stored in the memory, then we can try to override those content by some malicious code or malicious data. So then we will look at how buffer overflow can be used to, for example, run some extra function or run some malicious code. So a buffer basically is some memory space allocated for a variable, right? So when you write a program, you declare integer, character, or string, or character array. So basically the system will allocate some memory for each variable when you run the program, right? So the buffer is where you store the variable in the memory of the computer. So if you assign some value to a variable, then basically the value will be written to that particular location in the memory, right? So this is the definition of a buffer, right? So what is buffer overflow? Basically, buffer overflow means when you try to write data which exceed the capacity of the buffer. You have a larger size data than the capacity of buffer. In this case, then the data will overwrite other content in the memory. So this is the buffer overflow. Then the consequence also given in the definition. So if you overwrite the memory, then one consequence is you crash the system. But a more serious consequence is if you overwrite the memory with some special data, then you may do some malicious activity. For example, you may even gain control of the system. The attacker may gain control of the system by using buffer overflow by putting some special malicious content in the buffer, inside the memory, right? So let's first look at some simple example about the buffer and the buffer overflow, right? So this simple example actually illustrates the basic idea, but the more advanced attack actually is not as simple as this one. So this one, now you have a defined structure, right? So inside structure you have two variables. One is a character array, one is an integer. So integer will have 4 bytes, and this character array will have 8 bytes. So when you run the program, actually the program will allocate the buffer for this structure. So it will allocate 12 bytes. So 4 bytes for this character array, and then 4 bytes for this integer. So later, when you assign some value to the name or to the student number, then the value will be written to the location in the memory. Right. So this is a program which will assign some value to the variables. However, so when you run this program, you will find that the display actually is incorrect for the second student, right? So for the first student, everything is normal, but for the second student, the student number actually is some a strange number, random number. So why this happens? actually the reason is that we only allocate 8 characters for the name. This string actually is longer than 8 characters. Then what happens? So basically the extra character will overwrite the next part of the memory, which is the student number. Because in this structure, we put the character array together with the student number. If you have a longer string than the buffer size, then it will overwrite the next part, which is actually the student number. So that's why you will see some strange numbers for the student number. Right? So in this case, actually the location is important because this array is on top of the student number. So that means if you have more data, it will overwrite the next part, the next buffer for the student number. So this is one simple example to illustrate how buffer overflow can happen. And in this example, the consequence actually is you just get some wrong output. So it's not that serious. And in other cases, it can have a very serious consequence. Okay, so this is basically the one simple example to illustrate how buffer overflow can happen. Right? So in general, so buffer overflow is the result of a poor programming practice. So in particular, when we do not check the boundary of the buffer. So if we assign some value to a variable, so if we don't check whether this value exceeds the boundary, the size of the buffer or not, then we can have this problem. And in general, C and C++ programs, they cannot handle buffer overflow. So if you write programs in C and C++, then you cannot really. There are some also in the libraries, like C string libraries, there are some functions which are not safe. If you use those functions, they do not check the boundary for you, and then you can have a buffer overflow. So in C and C++, you must be careful because you can easily have a buffer overflow. But on the other hand, if you use Java, C#, and so on, so they actually will do some checking. So they can actually prevent the buffer overflow. But the C and C++, if you use this kind of language, then you need to be careful. Okay, so the consequence of buffer overflow, you can have like a wrong output, you can have a system crash, or actually you can gain control of the system. So you can run arbitrary code, any code, malicious code, on the victim's machine. So this can then cause damage. For example, the attacker may gain control of the machine and then insert some new users into the password file, shadow file, and so on. May also remove some users from the user account from those files and so on. Okay. Right. So in a typical example, so later we will look at, maybe tomorrow we will look at this typical example. So if say you have a program, your program is owned by the root user, and this program has this set UID, right? So if you still remember, if you have the set UID for a program, then anyone who executes the program will have the permission of the owner. So if say the owner is the root user, and the root user use the set UID to let other users to run this program. So in this case, if you have buffer overflow, then the attacker who actually may be an insider who can execute this program now can have the root permission. In this case, so if you have the set UID for this program, then this malicious user will have the permission of the root user. In this case, if you open a shell, for example, you insert some malicious code to open a shell. Then, if you have now you have the root permission and you open a shell, then you can do anything to damage the system. So in this case, we can have a very serious attacks. Right. So buffer overflow can also be used to override, for example, the privilege. For example, in some operating system, they just store the privilege after the username. So in this case, if a buffer overflow happens, you can use some special input to override the privilege. then in this case you can gain more privilege than expected. Right, so some examples. We look at one example, which is pin of death, but pin of death is quite simple of overflow. And some of the attacks we will see later in malware, actually, they are more advanced. So in particular, for example, some worms, they will use buffer overflow to spread themselves among the network. So basically, they will put them inside the buffer of the victim machine, and then actually inside the buffer there is some malicious code, allows the worm to replicate and spread itself to other machines. So in this case, actually the attack is more advanced. So you insert some malicious code and run the malicious code on the victim's machine. So this is basically some possible attacks in using buffer overflow. Right, so this is another simple example. So again, here you may think this example is silly. So anyway, it can illustrate the problem. So if you write a C or C++ function, so say you declare a buffer, as you now assign a string longer than the buffer, then actually you will overwrite the content after this buffer. So why I said this is silly? Because you may think people will not create a buffer and then use a larger index here, right? In reality, so this 512 can be replaced by another variable. Maybe the variable is the input from the user. So in this case, if the user is careless, then the user may use, for example, you replace this one by a j. J is supplied by the user. So in this case, j can also exceed the size of the buffer. So how to prevent the problem? Then a simple approach to prevent this method is you do some checking, right? So you do some error checking or exception handling. So you check the boundary before you really write the content into the buffer. Right. So now let's look at some the first part is some general idea about buffer overflow, the consequence, and some simple examples. So now let's look at some more complex example. And we will look at a stack overflow, and then heap overflow, and so on. So stack overflow is to use the buffer overflow to basically to overwrite the content in the stack. Stack is the inside the memory, some memory space we allocate for program or function. Right? So for example, when you call a function, when a function A call a function B, you will create a new stack inside the memory, and the stack will contain the local variable of function B, return address of function B, and so on. So once you finish the execution of the local this function, then the control will return to the calling function, and then the stack will be removed. That means the local variable will disappear. You cannot access the local variable in the function anymore. So, and then basically the control will return to the calling function, and then the calling function will continue to run. So we will look at how this process works, and then why the stack can have stack overflow. So some important condition for this stack overflow to happen. Okay, so this is basically the structure of the memory. So when you have a program, so basically you have this is the so-called process control block, PCB. So inside the process control block, you have some important information. For example, where is the starting address, physical address in the memory of this a program, and then you also have some other information stored in this control block. And then the program machine code is put here, and then you have the global data here, and then you have two structures to store the variables for the program. So one is called stack, one is called heap. Stack basically is to store the local variable, the static variables, and the heap is to store the dynamic variable. For example, you create a dynamic array. In this case, the dynamic array will be put in the heap, and then for the static array, it will be put in the stack. So the stack will grow in from top to bottom, and then heap will grow from bottom to top. And the spare memory will be in the middle, right? So this is the structure of memory when we run some program, okay? So basically now we will need to have some pointers pointing to the stack. We have a frame pointer which points to the starting position of the stack, and then we also have a stack pointer which point to the current position in the stack. So this the stack pointer will move when you actually run different command. Okay, so let's look at one example. Suppose we have a function P and a function Q. So function P will call function Q. So function Q may a function P may be called by the main function, for example. Main function will call function P. Function P will call function Q, for example. So here the return address is after you finish the execution of P, then the control will be returned to this address in the memory. So somewhere in the main function. For example, the main function, after you call the function P, you will execute the next command. So the control will be returned to the next command, and the address is put here in the return address. Return address means that after you finish the function, a particular function, then the control will be returned to that particular address to execute the next command. Right, so when function P call function Q, so here is basically the so-called frame pointer, so old frame pointer. So this will point to the stack of the calling function. So it will point to the stack of the function, for example, the main function, which calls the function P, right? So this is where we store the frame pointer of the calling function. So when in this case, when we try to call function Q using function P, so what happens? What will happen? So first, the parameters of function P passed to function Q will be written into the stack of function P. And then we will basically, after that, then the return address will also be put into the stack of function Q. That means you need to tell the machine after you finish Q where you should return. So basically, it will return to somewhere in the program P because the P calls Q. So after you finish the function Q, control should be returned to function P somewhere after this command calling the function Q. So this is where we return the control in function P after we finish Q. And then we create this buffer to store the old frame pointer. That means we store the frame pointer of function P in this location. The reason is because now if we are calling Q, you need to move the frame pointer to here to point to the starting position of the stack for Q. So later, after you finish the function Q, you need to move this frame pointer back to the starting position of the stack of P. So that's why we need to store the position here to this location, so that later, actually, we can relocate this frame pointer back to function P. Right. So this frame pointer points to the starting position of the stack. So after that, now basically you can allocate the space, the buffer for the local variables, right? So the stack pointer will always move. So every time you add a new item, so this is the same as the stack data structure. So you push the item, every time you add a value, you push the item, right? So every time you want to read some item, you pop the item. So this is how the stack works. Right, so you allocate the local variables for function Q, and then you can run, after you do the declare all the variables and so on, then you can run function Q. So after you finish the execution of function Q, then basically you need to set the stack pointer back to this frame pointer. And then basically now you will pop up the data here. So because this one is pointing to the stack of P, so you pop up the data here. Now you relocate this frame pointer back to here. So you pop up the data here and then you relocate the frame pointer back to this location. Right? So after that, then basically you can, after you reassign this frame pointer back to function P here, you can now pop up the return address. You can return the control to function P. because now this frame pointer is already back to the function piece stack, you can pop up the return address. Control now can be returned back to function P. So this is how we call a function. So we allocate the content in a stack. So every function will have its own stack and the return address. So one critical part here actually is when we assign the value for the local variables. The value will be filled in the reverse direction. So it will be filled in the reverse direction. So that's why in the next slide, the picture actually I turned this picture upside down. So when we assign value to the local variable, to the buffer, actually it will be filled in this direction. Right? So if we fill the content in this direction, then you can see the problem. So if you have a larger size input for the local variable 2, then it will overwrite local variable 1. So if you have a large size local variable 1, it will overwrite the return address. So if it's, the return address is overwritten, for example, if the return address is changed to some random value, then after you finish the function, you return to a random address, then the system will crash. And in another situation, you may return the control, you change this return address to a specific value, not a random value, but a specific value. So now this specific value can point to, for example, some malicious code in the memory, or another function, or another program inside memory. So in this case, basically you can execute another program, because now the control will return to that position instead of the original return address. So you can run some additional function, or you can execute some malicious code. If you know where the malicious code is inside the memory, you can set the return address to that position, then the malicious code will be executed. So in this case, it's not simply crashing the machine. So it will run some additional function or malicious code inside the memory. So here the critical one critical condition here is when we fill the buffer, we fill the buffer in this direction. That means when you assign a value for the local variable, it can overwrite the return address. Okay, so this picture illustrates this situation. So if you have, say, a buffer for 16 bytes, but if you have a longer string, then the return address will be overwritten, and then the system will crash. So this is a simple case, similar as in the pinning test. So if you have a packet larger than the buffer, then the system will crash. And one particular function here you need to pay attention is the string copy. So many C string functions, actually they do not check the boundary. So you cannot rely on this function to prevent the buffer overflow. So when they assign a string to a buffer, they don't check whether the string is larger than the buffer or smaller than the buffer. So you need to check it by yourself. So you need to check the size of the buffer and the size of the string to make sure this will not happen. Not just this function. So quite a number of C string functions, they have this problem. Okay, so basically in the previous case, we can have like a system crash, but the attacker actually can do something more serious. They can, for example, change the return address to a specific value instead of a random value. Right? So we can have some existing function. If there is some existing function in the memory, you can change the address to that function. Or if there is no malicious content inside memory, attacker can inject some malicious content. So where to inject? The buffer. The buffer, you can, inside buffer, you can, instead of filling the buffer with random data, you can put some malicious code. Then you just change the return address to the starting position of the malicious code. So in this case, you can execute the malicious code. Right, so this picture illustrates the idea. So instead of inserting some random data to fill the buffer, you can insert some malicious machine code So this is machine code, not the C or C++ like source code. You need to convert the program to machine code, the binary code, then you insert the binary code inside the buffer. You don't just insert some random data to fill the buffer. You put some malicious code here. And then you change this return address to the starting position of this code. Then after you finish the function, the control will be returned to this position, then this code will be executed. So in this case, in this example, this code essentially will open a shell. It will open a shell. After you finish the program, it will open a shell. So this is essentially the same, the problem that can be linked to the set UID. So this is a program owned by the root user. And the root user uses set UID to allow other users to run this program. So maybe this program is just a normal program. However, if the attacker can use buffer overflow to inject this malicious code here and change the return address, then after you finish this program, now the control will be returned to this malicious code. Then a shell will be opened. And because the root user uses set UID, so the ordinary user who executes this program now open the shell with root permission. Then actually you can open the shadow file, you can modify the shadow file, you can do anything. So in this case, the attacker can simply gain control. Because the attacker, if they can access the shadow file, they can create a new account for the attacker. They can even assign high privilege for this attacker. Then the attacker can take over the machine. Right? So this kind of attack can happen if you allow this kind of a buffer overflow to occur. Okay, so we can basically crash the machine to have a denied service, or you can basically run some malicious code to gain access of the computer. So some unsafe C function. So instead of not just besides the string copy, you also have other functions. So these C string functions are unsafe functions. Then we look at the buffer overflow. Right, so let's look at one program. So this program, basically, this again is an artificial program. So it's in reality, so the buffer overflow actually is not as simple as this program, but this is just for illustration purpose. So in this program, basically we have two functions, x and y. And the main function will only call x. So the inside main function will only call function x. And function y is a dummy function. So the purpose of this program is to illustrate, actually when we call the function x, if we can use buffer overflow to change the return address of x, actually we can call function y. So although y is not included in the main function, we can still execute this function y by using buffer overflow. So this is the purpose of this program. So in this program, actually we use some we use a stack pointer to print a stack. Actually, you can look at the content of a stack by using the stack pointer. So you can simply use this variable to print the content of the stack. So basically, the stack pointer will pop the data in the stack one by one, so you can see all the content of the stack. So this program will illustrate, for example, when we call the function with different inputs. So how the stack look like, so you can see the content of the stack, so that you can understand how actually this attack works. But in reality, of course, if you want to hack a program, the program will not print the stack for you. So that means that you cannot easily find the return address by looking at the output. You need to find the return address using some other method. So for this program is for illustration purpose. We just print the stack for you, but a real program will not print the stack to the attacker. Attacker cannot see the content of the stack. Attacker will need to use some other method to find the stack. You may ask how to find it. You can use the debugger. So if you can crash the system, you use a debugger. Actually, the debugger can tell you where the return address is for a particular function. So, but for this one, we just print the stack for illustration purpose. All right, so if you run this program using an input, say hello, so this is the string. So the program will show the content of the stack. So this is the content before you assign the value string. So it will print the starting address of function x. This is the memory location function x. This is the memory location of function y. And the content of the stack looks like this. And then after you assign the hello, this string to the buffer, then the stack will look like this. So you can see here hello has been written into the buffer. So 48 is H, 65 is E, right? So this is HELLO, and then you have the nonce character. So because in C and C++, you end a string with a non-character. So you have this 0, 0. This is the end of the string, basically. So you can see the direction actually is in this direction. So if you have a larger size input, it will overwrite this return address. Okay. So this is basically the return address where the control should be returned to the main function. Because in the main function, we only call function x. That means that after you finish the function x, the control should be returned to this address. This address is somewhere in the main function. However, if we can change this address, for example, to this address, then instead of returning the control to main function, it will return the control to a function y. Function y will be executed, will be run. So we will see how this can be done later. So if you simply try a large string, bigger than the buffer, then you can see the content of the buffer now becomes this one. So 41 is A, the uppercase A. So you have all the A here in the buffer, then you will receive an error message. So the system will basically abort, will crash. So you need to terminate the program because now the return address is overwritten by this long string. Right. So you can also see now the offset here, it tells you actually the return address now becomes this string, which is some, basically from the system's viewpoint, this address is invalid address, then it will abort, right? So this will crash the program, right? So if you run just a shorter string, then you can see the buffer again, right? So actually you can test when the buffer overflow happens. Then you can identify actually where is the return address. So you can test different size for the input. Then you can see where the crash happens. Okay. So here this slide is just to remark that pay attention to this non-character. So this is the end of the string, right? So even if you have the buffer same as even you have a string same as the size of the buffer, you will still have a crash because you have an extra non-character here. It will still overwrite the original return address. So now how to run this function y? So you need to, instead of using like a random string, you need to use some special value. So what special value should be used? Actually, you should use the return address, the address of y. That means you fill the buffer with a string, and then at the position of the return address, you fill in the address of function y. So that means after you finish the execution of x, now the control will be returned to this address, and this address is function y. Then the function y will be executed. So you will see this string printed on the screen. That means the function y has been executed. So although the main function does not call function y, by changing this address, actually this function y will be wrong, and then you will see this string printed on the screen. So this is basically the string that will be printed by function y, right? Of course, in reality, you may do something else instead of simply printing a string here. So here, pay attention. So when you try to write the content into the return address, so here you need to use this hexadecimal format, right? So because all the addresses, all the data in the stack, they are represented in hexadecimal. And also, when you fill the when you input this address, so here you need to use the reverse order of the address, because remember when we fill the buffer, it's from right to left and from top to bottom, right? So if you this is like the address is like this, that means because it's from right to left, so you need to put 28 first. This is 1 byte. 13 next. This is 1 byte. 40 next. This is 1 byte. Then you have this address, which is same as the address of 1. So here the order actually is the opposite of the address, because the input is given when you fill the buffer is from right to left. So that's something you need to pay attention. Right. So this is one example to illustrate how you can actually run an additional function, which is not supposed to be run by the main function. But as I said, this is an artificial example to illustrate how it works. In reality, actually, you cannot really see the content of the stack. Yes?
Can you run like push pop move instead of being uppercase B characters in this?
Oh, so basically you can put some like code here. So you can put that's what we will start. We will look at probably tomorrow. So instead of this example shows that you run some function y which already exists, but actually you can put some code here. You can put some malicious code here, and then you can change. For example, you put like these 2 lines. You can put some malicious code here. Then you change the return address to this position. Then you will run this code here. Okay? Yeah, so it will be discussed later. You can do such kind of attack. So you can insert malicious code inside the buffer. Instead of putting some dummy dummy string here, you can put some machine code here, and then you change return address to this position. Then the machine code here will be executed. So we will look at some example later when we look at like the shell code, like and also heap overflow. Actually, you can insert malicious code and run the malicious code. And as I said, here is just an artificial example to illustrate the idea. So in general, you cannot see the content of the stack, because a normal program will not print the content of the stack for you, right? So if you have a normal program, then how to find the return address? As I said, it's not really that simple. Actually, it will need some effort. So you first need to find a way to, like for example, crash the system. In this case, if you crash the system, then you can run the debugger. If you run the debugger, then actually you can see the content of the stack. So in this case, you can identify where the return address is. So it still needs some work to find out the return address and the structure of the stack in reality. So if you are only given an exe file, you need to use some additional tool to identify the return address and the structure of the stack. But for this example, because we print the content of the stack, you can easily identify the content. You can see how the content of the stack changed. Okay, so you may ask then, if I have a program, and the program is used by different users. So suppose this code actually works in one machine, because I changed the return address to the address of 1. But if I run the program in another machine, then if I use the same piece of code, will it work? Maybe because another machine, then the location of y is changed. So if you use this code, it will not work. But actually the answer is no, the code will still work. Why? Because the address in the program is the so-called logical address. So it's not the physical address. So the physical address, if you studied OS before, operating system before, you know, I just actually mentioned in the PCB, process control block, you have the starting position of the physical address. So the real physical address for a particular buffer is the starting address plus the logical address. So the logical address is just the offset. So you have the physical address, the starting physical address, and then the logical address. You plus these two, you get the physical address of the particular buffer. But in the program, we look at here, the address here, they are logical address. So that means in different machines, the logical address are the same. Only the physical address, the starting physical address will change. So even if you run the code in a different machine, this attack will still work. So basically, that's illustrate that if you can exploit the vulnerability in one program, anyone who runs this program, actually you can attack that machine. So it doesn't matter where the program is executed. Okay, so that's basically for the one example how to do something else beyond the crashing a machine, right? So you can do something else. And probably we will look at the other content of buffer flow tomorrow. Tomorrow we will see the student just asked how to put some malicious code and how to run the malicious code by changing the return address. So we will look at some example.